In this video, we'll learn about op-amp non-idealities, slew rate, and offset. The slew rate is the maximum rate at which the output of an op-amp changes when a large differential input signal is present. This is a nonlinear phenomenon. For example, if you consider a linear system step response with a large differential signal applied, let's say it's a well-compensated op-amp system, and compensated with near 90 degrees of phase margin, then we would expect exponential settling with no overshoot, something like this dashed line shown here. However, we know that for exponential settling like this, the rate of change at the output voltage would be fastest at the start of the exponential here. And that rate of change may require capacitances in the circuit, or perhaps at the output node, to be charged or discharged quicker than the op-amp is capable of. Usually this is because some bias currents are being fully used up, just charging or discharging a capacitor, leaving nothing to keep the transistors biased at their proper operating point. So something inside the circuit likely saturates. In any case, the slew rate sets the limit on the maximum rate of change at the output. So the actual response to a large step input would look something like this. At first, you would see the output increase with a constant slope equal to the op-amp's slew rate. Then, at some point, the remainder of the settling behavior can be done, let's say, with an exponential settling response without exceeding the op-amp's slew rate. And so at this point in time, exponential settling would resume and the output voltage approaches its final value asymptotically. So this is clearly a nonlinearity. This is not how a linear system would behave. On the other hand, even with an op-amp having a slew rate limit, if all the steps that are applied to the input of the op-amp are small enough, then we will indeed see the op-amp's linear behavior, for example, exponential settling, such as shown here. So slew rate limiting only arises when the input step is large enough to demand it. This example considers the response of an op-amp circuit in the presence of slew rate limiting. So let's say that the feedback amplifier is compensated to have an approximately first order response with a time constant specified here and a maximum slew rate of 1 volt per microsecond. Then we're asked to consider what's the settling time for a specified accuracy with a 10 millivolt output step. Well, it turns out that if you find the maximum slope required at the output to accommodate this 10 millivolt output step, it's less than the op-amp's slew rate. So therefore, no slew rate limiting is observed with a 10 millivolt step at the output, and we can find the 99% settling just as a function of the time constant. In this case, you're asked for 99% settling, so that turns out to be 4.6 time constants. Um, on the other hand, if you consider what happens when a 1 volt output step is demanded of the op-amp, then we would see slew rate limiting arise because the first part of exponential settling with a 1 volt step would be faster than the op-amp slew rate. So slew rate limiting occurs and the output increases with a constant slope equal to the slew rate 1 volt per microsecond. It turns out that once the output of the op-amp reaches 0.8 volts, the remaining 200 millivolts can be settled exponentially with the time constant tau without exceeding a slope of 1 volt per microsecond. So for the remainder of the settling behavior, we see first order single time constant exponential settling with that time constant. And then we can find the specified settling time, 99%, or in this case, 0.1 millivolts is actually finer than, more accurate than 99% settling. You can find the final settling time as the sum of the first 0.8 microseconds during which the op-amp was slew rate limiting, plus the amount of time required for the final exponential settling to settle within the specified 0.1 millivolt tolerance. Now that we know what slew rate limiting is, let's see how we can find the slew rate limit of an op-amp that we're already familiar with, the folded cascode op-amp shown here. First, we're going to consider what happens ignoring transistors Q12 and Q13. We'll reintroduce them later. So typically the way you can think about what happens in slew rate limiting is to consider an input step that has a large enough amplitude so that the diff pair completely switches. For example, let's consider the case of a large positive step so that a large positive differential input appears at Vn, large enough so that Q1 is completely off and Q2 is therefore conducting all of the bias current I bias 2. Now there's two possibilities we need to consider. One is that I bias 2 is greater than the bias current ID4, which is the same as the bias current at ID3. The other possibility is that I bias 2 is less than ID4. These give rise to two slightly different slew rates. But once you understand the premise, you can consider the other case pretty straightforwardly. And the more common case, I'd say, is that I bias 2 is larger than the bias current through ID4. It really depends what fraction of the overall um, bias current through ID4 is going through the diff pair versus how much of it's going to the output stage transistors Q5 and Q6. In any case, let's consider the case I bias 2 is greater than ID4 and 3. First, you'll notice that since Q1 is off, all of the bias current ID3 flows this way because no current flows down through Q1. So ID3 goes this way and down here in its entirety. On the other hand, I bias 2 is so large that it draws all of the current ID4 and then some actually. So therefore, there's absolutely no current flowing this way. Q5 turns off. These transistors are all off. There's a mirror there, so these transistors are conducting zero current. So as it turns out, it's all of ID3 flows through here in this condition and goes on to the capacitance CL. Therefore, the output just increases linearly with a slope of ID3 over CL. And ID3 is the same as ID4, of course, because they're simple current mirror. They're matched transistors in the same current mirror. So that's the situation. And you could do a similar analysis to see what happens if you apply a large negative step, and you would find the very similar result. The slew rate would be the same on the way down. It would just be a negative slope in that case. Again, it would be given by ID4 over CL. So this expression holds in this case. I bias 2 is greater than ID4 and 3. Now, a problem with this op-amp in this case is that with I bias 2 exceeding ID4, which as I said is a normal case, this voltage here would be pulled down by I bias 2 faster than ID4 could supply it. So the voltage here would actually drop and continue dropping down, 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 pushing Q2 into triode ultimately, and even the current source I bias 2. The voltage at this common source node here would also get pulled down eventually because I bias 2 is larger than the current supplying at ID4. So that node drops all the way down and it kind of compresses the voltage across this current source I bias 2 until some transistors in there enter into triode, and then finally that current source is not working properly and the bias current actually will decrease until it finally is equal to ID4. And then at that point we've reached a steady state, but all these node voltages have dropped very, very low. So a problem with that is that when the op-amp leaves slew rate limiting and wants to resume linear operation, all these bias voltages are really messed up, and it will take some time for those voltages to be charged back up again by the bias currents ID3 and or ID4. restore the transistors to their proper operating mode. So it can take a little bit of time for this op-amp to recover from slew rate limiting. So that's a significant challenge. So to address that, let's consider, again, let's reconsider this circuit, but this time considering the impact of the transistors Q12 and Q13. Okay, just going to tidy this up here. So first of all, let's recognize that in normal operation, Q12 and Q13 are off. So when we're not in slew rate limiting, there will not be sufficient gate source voltage on Q12 and Q13 to turn them on. So they really have no effect until such time as we see a large step. And then once the op-amp tries to enter slew rate limiting, let's again consider the case of a large positive voltage arising at Vin, large enough so that Q1 turns off and all of I bias 2 is conducted this way. And then, as we said, this node voltage starts to drop. And at some point then, the gate source voltage of Q13 would exceed its threshold voltage and it will turn on. At that point, a couple of interesting things happens. First of all, Q13 can then supply some extra, the missing current that makes up the difference between ID4 and I bias 2, and in effect prevents this node voltage from dropping much further, right? So it acts under slew rate limiting, one of those two transistors effectively turns on and kind of clamps that voltage and prevents it from getting pulled all the way down near ground. And that therefore allows the op amp to recover more quickly from slew rate limiting because the bias point is not as messed up. So where does this current come from? Well, if you follow the trail of the current, you will recognize that the only place it could come from is in fact through Q11. So now a secondary benefit of these transistors is that again under slew rate limiting, Q13 turns on and the bias current through Q11 therefore temporarily increases. Normally it's just I bias 1. But during slew rate limiting, there's an additional component to Q11 equal to ID 12 or 13, depending on whether we're in positive or negative slew rate limiting. In this case, it's ID 13. So that extra current flowing through Q11 then gets mirrored over to Q4 because Q4 is just the current ID4 is just a mirrored version of ID 11. And that has a secondary benefit of temporarily increasing ID4, which actually boosts the slew rate and can boost it significantly. So so now you know what these transistors Q12 and Q13 they are there primarily to improve the op-amp's performance in slew rate limiting. So let's next consider what can be done to improve the slew rate of a folded cascode op-amp. Let's say you design an op-amp and compensate it to have sufficient phase margin, but unfortunately the slew rate is insufficient. What can you do? What changes to design can you make to improve the slew rate, assuming, for example, you can't change the load capacitance here? So just looking at the expression for slew rate, ID4 over CL, clearly one thing that can be done is just to increase the bias current ID4. Now, you know, even in the presence of Q12 and Q13, the slew rate would be slightly greater than the expression given here, but nevertheless, if you keep all, the load capacitance the same, and you just, for example, double all the bias currents everywhere in the circuit, you double the ratio W over L for all transistors in the circuit, excluding Q11, then you would just have more bias current to charge up the load cap. You'd retain the same gain, the same phase margin, and the only thing that would happen is you'd be, in that case, doubling the power consumption. So that's one way to improve slew rate. Not too surprising. Increasing power consumption generally is one way to improve lots of things about an op-amp simultaneously. You can improve its noise performance and often it's bandwidth. Um, but let's say you're already consuming all the power that you're allowed to in this design. Your boss or the specifications is limited maximum power consumption, and the slew rate's still not enough. Then what can you do? Well, one approach you can take is if CL includes a compensation capacitor. Um, let's say part of CL is formed by an explicit capacitance that you've added to ensure sufficient phase margin. Well, you could reduce or eliminate that extra compensation capacitor. That would obviously reduce CL and boost your slew rate without adding any extra power consumption. Unfortunately, that compensation capacitor was presumably there for a reason, and that was to provide your desired phase margin. So by doing that, you would lose some phase margin. And in order to get that back, um, there's a number of different things you can do, but one way you could do that is reduce the GM of the input stage, GM1 and 2. Now, you can't reduce GM1 in this case by reducing bias currents, because then that's going to have a knock-on effect of reducing your slew rate, which is the whole thing you're trying to avoid here. You're actually trying to increase the slew rate. So you want to keep all the bias currents the same. So how do you keep the bias currents the same and still reduce GM1? You can bias it with a larger V effective. So keeping the bias current the same, you would do that by decreasing the ratio W over L. So if you do that, you reduce GM, and since you've reduced the load cap, remember that the unity gain frequency of this amplifier, assuming it's compensated for phase margin near 90 degrees, is something like the GM of the input diff pair over CL. So you've reduced CL in order to improve the slew rate, and um, you can then reduce GM1 and 2 commensurately by biasing it by sizing them to have a larger V effective for the same bias current, and that would keep the unity gain frequency the same. And assuming the second pole frequency didn't move as you did all this, which it shouldn't, because you haven't resized any of the transistors that are likely to affect the second pole frequency or change any of their bias current. So the second pole frequency probably hasn't changed. So you've probably got the same phase margin that you had before and just a higher slew rate. However, one thing you've given up this way is you've decreased the DC gain. GM times R out. Also, you're likely to have made the op amp have a higher input referred noise by doing this, as we'll discuss in the section on noise. And finally, of course, this option is really only available to you if you have the ability to somehow decrease CL. That may not always be a possibility. Next, let's consider another non-ideality, amplifier offset. So we expect that for an ideal amplifier with zero differential input, we would expect zero output. But in practice, there's going to be some non-idealities, mismatch, and so on that will result in a finite output voltage even when the differential input is exactly equal to zero. So the output voltage that arises when with zero differential input is referred to as the output offset, but usually what's of more interest to us is the voltage that we would have to apply at the input in order to give rise to zero output at the offset. This is usually a small voltage, of course. In fact, it's typically the output offset divided by the gain of the op amp, which is a very high gain. Um, but that's usually what we'll see specified. Now I've pictured here op amps with a differential output, which we'll discuss. If there's a single-ended output, you can just think of the offset at the output as being, its deviation away from its nominal output level. So we can model an op amp with offset by introducing a DC voltage in series with its input. In general, you can model the offset in series with either input terminal, but it may be more convenient to do so um, at whichever, at one or the other, depending on the circuit configuration. The idea here is that if you have a real amplifier that has a finite offset built into it, we can just replace it with the circuit in this red box that is an amplifier with the same gain and all else the same, except zero offset in series with this input referred offset voltage DC source equal to VOS. In a well-designed op-amp, offset is likely mostly coming from mismatch between transistors that should be nominally matched. So for example, any current mirror in our circuit will be subject to mismatch, and we've already discussed how mismatch in transistors is affected by the size of the devices. So if offset is an important specification for your amplifier, you may wish to design current mirrors to use very large transistors, and there's also benefit to biasing them with high V effective. Another source of mismatch in op amps is mismatch in the differential pair transistors, so the input pair specifically. So when it comes to differential pairs, we've discussed the influences of device sizing on mismatch. Again, there's benefit in using very large transistors with a large area, W times L. And we find, especially in the typical scenario where we've biased the input pair transistors of the op amp with relatively low V effective to get the most transconductance for a given bias current. Again, in such cases, we will expect the threshold voltage mismatch of the transistors Q1 and Q2 to be dominant. In fact, it's the input pair transistor mismatch that will often dominate the overall offset of our op amp. So again, looking at our folded cascode op amp, because any offset that arises at Q1 and Q2 is essentially occurring right at the input, its mismatch between these two transistors is quite often dominant. If you think about mismatch that may arise between other transistors, such as Q3, Q4, Q5, Q6, these current mirror transistors down here, their impact arises closer to the output, and therefore when we think about their impact on the input referred offset, we have to divide by the GM of Q1 and Q2. And since we've likely sized transistors in the op amp to try to maximize GM1 and 2 for a given bias current, so it's quite often the case that GM1 and 2 are relatively large, and therefore the input referred offset contribution of all the other transistors is divided by that large GM and therefore smaller than the mismatch inherent in Q1 and Q2. Of course, all this should be taken with a grain of salt. For every rule of thumb like this, there's always going to be exceptions. Um, Now, in the case where we've um, designed the op amp so that GM1 and 2 are larger than any other transconductances in the circuit, then we've probably also biased them with a very small V effective, and in that case, it's quite likely that their threshold voltage mismatch dominates over other mismatch contributions. So, in summary, quite often the largest contributor to offset in a well-designed op amp like this will be mismatch in the threshold voltage of the differential pair transistors, and that is directly input referred. For example, if these transistors have 1 millivolt threshold voltage mismatch, that's going to give rise to 1 millivolt input referred offset right away.